Lecture video, we're gonna talk a little bit about applications of our exponential functions. So in the last video, I showed y'all how to solve the basic elementary exponential equations. So here we're gonna take a look at some application. So I group these application problems into objectives. So the first one I want to show y'all is the models of population growth. So the population growth function, here I got two of them. Okay, first one is called pizza t equal to pizza naught times base a to the t power, or we can have pizza t equal to pizza naught times e to the kt power. So this e is just another base that we can use. So normally the base a we use is, number that are greater than 1 and not equal to 0. So this model is what we're gonna focus on a little bit more right now. We will introduce the base e in a different lecture video. So what are these notation represent? Pizza naught is referring to the population at the time 0, or the initial population. Pizza t is your population after some time t. Okay, the letter a is referring to your growth rate of the population. So if this number in front of the t is a negative, that means we have a that means we don't have a positive growth. Now our population is actually decreasing if there's a negative number. Alright, this k, which I will explain later on again, is called the exponential growth rate. Okay, exponential growth rate. So when we look at this base e, we will actually talk more about this letter k here. So the front one is what we're going to focus on here for a moment. So let's give it a try, okay? Let me copy and paste this, because this is the model that we are looking at. Alright, so consider a certain species of deer is to be introduced into the forest, and the wildlife expert estimate the population will grow to pizza t equal to 206 times 4 to the t over 2 power, where t represents the number of years from the time of the introduction. So the question asks, what is the quadrupling time for this population? Quadrupling time is looking for the time that the population will quadruple. So if I would line up my model to what this problem is asking, alright, so my initial population is 260 years. Okay, my growth rate is 4 to the t over 2 powers. So what is a quadrupling time? That means my population will quadruple from the initial population, and we're looking for the time that will occur. So quadruple, okay, simply means 4 times my initial population. And I'm going to solve this problem in a very particular way, which is equal to my initial population times my growth rate 4 to the t over 2 power. T over 2 can be written as half t. Alright, so this half is a positive number, so I do have a population growth. Okay, my population will increase over time. So the question asking when my deer population will quadruple. So if you look at this equation, the left side and the right side is only one term and one term. So this whole equation is only consists of 2 terms. So to bring down the half t, okay, the variable being on the exponent, what I can do initially is divide both sides by 206. Oops, sorry. Let me try this way. If I divide both sides by 206, since I only got 2 terms, one on each side, all I can do here is divide my coefficient. So I'm basically trying to peel off all these stuff in front of the variable. So 206 over 206 will cancel out. That will just simply leave me with a 4 is equal to 4. This becomes 1 to the half t power. So the 4 means 4 to the first power. So when the base are the same and the base are equal, we set our exponent equal to each other. So if I divide both sides by a half, my time will equal to 2 years. Okay, so that means what is a quadruple in time? It will take 2 years for my deer population to quadruple. Alright, now the question asks, how long will the population reach 3,290 deers? So again, okay, looking for the time when the population of the deer after some time t reach 3,296. So my future population of my deers after so much time t, I want it to be 3,296, which we will set equal to the initial population times my growth rate to the half t power. Alright, do the same thing. Computation for these problems are very simple. There's only so many steps we take. So to isolate my variable up here, we need to divide both sides by 206. So 3296 divided by 206, that will give me 16. So that's 16 equal to 4 to the half t power. Alright, I know I can make my 16 into a base 4, so that will be 4 squared equal to 4 to the half t power. So once the base are the same and the base are equal to each other, we set the exponent equal to each other. So to get time by itself, I will divide both sides by half. So that will be 2 divided by parenthesis 1 over 2. So my answer will be 4 years. So 4 years, 4 years later, my population will reach 3,296 years. Alright. Let's try another one. This one's a little bit different because this one doesn't give me a model first like the previous problem. So we got to be able to read this problem and then figure out what is actually our population model. So the problem says, in an effort to control vegetation overgrowth, 90 rabbits are released in an isolated free area. In the isolated area free of predators. So my 90 rabbits is my initial population that I'm introduced. Piece of null goes right here. After 2 years, so this is after some time t, it is estimated the rabbit population will increase to 810. So that means after 2 years, time is 2 years, the population will actually become 810. Assuming exponential population growth, what will the population be after another 9 months? Okay, so the question is asking what the population going to be after another 9 months. Another 9 months after the 2 years. So we got to use this information, okay, to help us to write out the model before we can answer the question itself. So my initial population was 90 rabbits times my exponential times my population growth rate to the second power, because after 2 years my population reached 810. So basically this problem, I'm looking for my growth rate. That's the only variable missing. So again, divide both sides by 90 to isolate my variable a to the second power. So that will give me 9. So to get a by itself, I will take a square root on both sides. And normally when we take a square root on both sides, my answer is positive or negative 3. But here, it problem says assuming exponential population growth. So since I'm having a growth, my growth rate got to be positive. So I'm only using a positive 3 here, not a negative. Alright, so once I find my base, basically what the problem now become is my future population. Okay, my population after some time t is now going to equal to the initial population 90 times my growth rate 3 raising to the t power. Okay, so that will be my model for my growth rate, just like this one right here. So now we can begin to answer the question. So first thing we do is find the missing variable so we can write out our model. Therefore we can answer the question itself. What would the population be after another 9 months? Another 9 months after 2 years. So that was 2 years and 9 months. 9 months out of the year is 3/4. 9 out of 12 is another 3/4 of the year. So that would be 2.75. Oops, sorry. So another 9 months means another 2. That means we add another 0.75 of the year to it. That will equal to 90 times my growth rate 3 raising to the 2.75 year. Alright, let's put this in a calculator. Initial population times the growth rate raising to the 2.75 years. Round to the nearest rapids, there'll be 1,846 rapids. So this is very crazy because 2 years is only 810. Another 9 months later, you will actually grow over 1,000 rapids. Okay. All right. That's all this problem is. Okay. Let's look at another one. Let's practice this. Okay. Practice this. A lot of times, if a problem does not give me the model, I got to read this carefully and figure out what the model is. So this is a very interesting problem. Assume a current world population of 8 billion people. Right now, I think we're a little bit over 7 billion on Earth as of 2017. Assuming a current world population of 8 billion people, an annual growth rate of 1.8% per year. In a worst case scenario of exponential growth, okay, so I'm having a growth, what would the population be in 32 years? Okay, so let me go down here, copy my model here. So this problem is a little bit trickier because my initial population right now is 8 billion. Let me write out the model. Times, okay, I have a growth rate of 1.8% per year. Now we know 1.8% is 0.018 in terms of a decimal. So this is my growth rate, 0.018. So what a lot of students will do here is put growth rate as 0.018. Okay, raised into the t power, but that's incorrect. And the reason is the initial 8 billion people will still be carried into the following year. So I'm actually taking the entire 100% of the 8 billion plus my 1.8% growth. So that means I'm actually having 101.8% for the next year computation. Think about this. My growth is 1.8%. That's right. So once I figure out what my growth is next year, I still have to add on to the original initial 8 billion. So what we can do easily is take the entire 100% of the 8 billion people and add on my 1.8% growth. So that will quickly give me what the next year population without having me add 8 billion. I'm adding my percentage rather than adding the actual number of people. Alright, so this is actually going to be 1.018 to the t power. Okay. This is a little bit different way of thinking about this. I have a positive growth. Once I use 8 times 0.018, that number will only be the growth. But actually how many people is after 1 year, I still got to add the 8 billion. So rather than add the 8 billion people to my growth, I can just add them in terms of percentage. 100% plus another 1.8% growth will be 1.08 or 101.8%. So I'm looking for 32 years later. So that will be 8 times 1.018 to the 32 power. So that means, okay, my answer will have the initial 8% already in it. I don't have to add another 8%. 8 times 1.018 raising to the 32 power. Okay, round to 2 decimal places. So that'll be 14.16 billion people. Now, can I do 8 times 0.018 to the 32 power? Then add 8 billion and then times my 8 billion. Excuse me. Add my 8 billion, sorry. No, can't really do that. Doesn't actually work that way. Because without taking the initial, see, what makes sense is 8 times 0.018 to the first power. After 1 year, this is the growth. Plus 8. So the after 1 year will be 8.144 billion people. Then you got to do it again, taking that same number times the growth 0.018 to the first power, then plus the 8.144 to give you the population after the second year. Okay, so that computation kind of accumulates itself. You got to do it for 32 times. So it's easier just to compute with 100%. Okay, 100% of the 8 billion people will be taken into the growth percentage and use the 1.018 to compute the 8%. Okay, it's a different way of thinking about it. If you take 0.018 to the 32 power, that decimal is getting smaller and smaller and smaller. That's why it doesn't work if without the 1 being in there. Alright, let's take a look at another one. This one, give me the model. Alright, see that negative sign in my model? Okay. So, being a negative, so that means I have a decrease in population. Now, my base is not using it's not using other numerical number. I'm using a base E right here. So this problem says the population of a certain inner city area is estimated to be declining. That's what that growth rate is, negative. According to the model, where t is a number of years from the present, what does this model predict the population will be in 6 years? So let me copy and paste this. So this particular model using the base E, alright, so if you're matching up the model with this, if you match up with the models here, what it's trying to tell you is the initial population is 446,000, okay, times the base E to the negative KT power. So the K is negative 0.014, so I have an exponential decay, exponential decrease in population. So I want to find what's the population after 6 years of decrease. So that'll be 446,000 times E to the negative 0.014 times 6. Okay, run to the nearest person. Alright, let me show you how to key this in the calculator. 446,000. Alright, there are two places we can use the number E. I can do second E to the X, or second just a number E right here. But since I got to typing things after the E on the exponent, I can use second E to the X. So now it says E to the what power? So in that parenthesis, we put negative 0.014 times 6, close the parenthesis. So that means our calculator will do figure out the exponent first before E will raise to that power. So 6 years later, that will be dropped down to 410,066 people. So let me use this opportunity to jump a little bit. I'm gonna go to this objective right here. So what is a number E? A number E was actually named by the mathematician Leonard Euler back in 1741. So the number E, just like the number pi, there are different ways to derive the number E. So if I do second and the division button, that will tell me what this irrational number is about. So the one we just key in, 446,000 times my base 2.718 something to that kind of power. So the number E is just like a base 2, just slightly bigger than base 2. It's about 2.7-ish. Okay. So it's just another base we can use, okay, other than the number that are bigger than 1 or not 0. Alright, let's try another one. Population growth or population decrease. So this example says Wilbur is working in a lab testing bacteria population. So anything that grows, any live thing that can grow is considered as a population growth model. After starting out with a population of 403 bacteria, he observed a change in population and noticed that the population triples every 34 minutes. Okay, triples every 34 minutes. Let me copy my thing here. Find the equation for the population P in terms of T in minutes. Run the value to the 3 decimal place. Okay, so let's see what we got so far. Starting out with 403. So 403 got to be the initial population for the bacteria. The change in population is triples every 34 minutes. So every 34 minutes, so the first 34 minutes population tripled. So that will be 3 times the initial population. So 3 times the initial population, whatever the number is after the first 34 minutes. The next 34 minutes, it will triple again. Okay, so we can use that concept, and knowing that after the first 34 minutes, population will be 3 times that, 3 times the initial. So I can use that idea to help me define the base A. What's my growth rate? So same calculation, divide both sides by 403. 403 will cancel out. So that will be 3 equal to A to the 34 power. So to find my growth rate, I will take a 34th root on both sides. Now, I don't think we ever done something like that before. So 34th root. Remember, during the review, we mentioned that fraction exponent becomes the radical. Denominator determines how many root we are taking. The base A is raising to the numerator power. So when I take a 34th root on both sides, my m, my base 3 inside the 34th root is to the first power. My root is 34. So instead of taking a 34th root on both sides, I can actually just say this is 3 to the 1 over 34 power. That would be the same thing. So 3 to the 34th root is the same thing as saying 3 to the 1 over 34. Denominator determines the root. The numerator tells you that the base is raising to that power in the inside. Okay. I'm not using negative because 34 is an even root. I'm not using negative because the problem does say what? Population triples, so I have a growth. So this is going to be 3 raising to the parenthesis 1 over 34 power. Round to 3 decimal places, 1.033. So my base A is 1.033. So this step wants me to find the equation for the population P. So that means my model the population after some time T will equal to the initial population, which is 403 bacteria, times my growth rate 1.033 to the T power. So Mrs. Chen, what happened to my 34 for T? Well, the 34 was only used, okay, to help me to find the growth rate A. And the 34 was actually for that population. Okay, so that 1 point something, just like this one right here. Okay, you need to take 100% what you start out with plus the growth rate Okay, so you actually have over 100% raising to the t power. All right, find the population after 2 hours. Remember now, t was in minutes. 2 hours will be 120 minutes. So my population will after 120 minutes. Remember now, it triples every 34 minutes to give me the growth rate 1.033 something. So this is going to be 403. It's an initial population times my growth rate, raising to the 120 power. Alright, we're on to the nearest bacteria. So that will be 19,831 bacteria. Okay. All right. Besides population growth, because these seems like population growth without bound. Another type of population growth is called. Oh, I didn't have it in here. Oops, sorry about that. Let me add in here real quick. Another type is called limited growth. And this is a very good example for talking about virus and things like that, you know, catching a flu. So this function, okay, models a number of people in a small town who have caught the flu t weeks after the initial outbreak. Okay, so limited growth. How many people were ill initially? So that means initial time must be 0, because that's when the outbreaks begin. When they first begin, is the number of weeks is 0 weeks. Because if you say initial is 1, that's actually referring to 1 week after the initial outbreak. So for the initial outbreak, the time is 0. So again, using the base E here, I'm going to put 0 where that time is. That will give me 11,000 over 1 plus 999 times e to the -0 power. -0 is just 0. So I'm going to do this in pieces, okay? I'm going to do e to the 0 power. E to the 0 power is 1. 1 times 999 is 199. Excuse me, it's 999. 999 plus 1. So 1 times that is that. That plus 1 is 1,000. So if I take 11,000 divided by 1,000, okay, initially, how many people were ill? 11 people were sick. Okay, so the answer T is referring to the number of people get sick after T weeks. So how many people have caught the flu after 4 weeks? So now I'm going to put a 4 right here. So that'll be 11,000 over 1 plus 999 times e to the -4 weeks. Okay, I want the denominator to be calculated at, together first. So what I'm going to do is type in 11,000 divided by parenthesis 1 plus 999 times e to the -4. Close parenthesis for the exponent. Close the parenthesis for my denominator. And that will be 570 people get sick then. So what's going on here is, as the time keep going, okay, I'm gonna put this actually in the under y equal. Why does it call it a limited growth? Negative x power. There's no t, I gotta use x. Close it, close it. So here is my exponential function. Okay, it looks like it's going upward. That's true. But if you look at the table, the y value represents how many people gets the flu. Okay, so for 4 is 570 people, but the next week, the end of next week, it actually becomes 1,422 people. So as the weeks goes on, these numbers is shooting up, shooting up, shooting up until week 17, 18, 19. Doesn't change. The y value does not get changed. And the reason is, it means everybody got sick in a town of 11,000 people. So once everybody got sick, then the flu stops. Okay, you cannot actually infect any more people in that town, because once everybody's sick, then that's it. Because virus, okay, the idea of a virus is attacking. It's actually trying to get the healthy people sick. But once you caught the flu, that means you got it. You cannot get flu again when you have a flu. Okay, so you cannot get sick twice at the same time. Okay, flu only attacks healthy bodies, and that's basically the idea of that movie called the World War Z, where the Brad Pitt was in. Okay, talking about treating the zombie apocalypse like a virus. The virus is always seeking for healthy host, healthy cells, but once somebody who already terminally ill, it cannot get another virus into that body. Okay, so once everybody's sick, then the growth is limited. Okay, you're only limited by how much population that is. All right. Now another type of exponential growth is called the radioactive decay. This is a very interesting problem. Something called a half-life. Okay, half-life means half of its initial amount. Okay, so the half-life of a titanium-51 is approximately 5.76 minutes. Okay, so determine the base A so that this model describes the amount of a titanium-51 after left. How much is left after T minutes, where ethanol is the initial amount at the time 0. So it's weird, for any substance, initial amount is not really saying it's 100%. Radioactive decay is a way for us to date back. Okay, is for us to date back how old something is. Okay, by knowing the half-life of a particular substance. So I'm going to look at this thing and think, okay, the problem says a half-life, so that means in the future, half of its initial amount, okay, whatever is left, half of its initial amount will equal to the initial amount times my base A, my growth rate or decay rate, to the T power. And what's my T? My T is 5.76 minutes. Because after 5.76 minutes, then what I have left with is half of its initial amount. That's what I mean by half-life. Half the initial amount, okay, is half the time. So we use very particular elements the type of element that we know what the half-life is to date back, how old something is. Alright, let's find my base A. Let's see what my growth rate is. So the way I've been showing you how to do the computation, divide both sides by the initial amount, okay, whether it was that 403 bacteria or other problems. The first step is divide both sides by the initial amount, so that will cancel out. So that means the half-life is equal to my base to the 5.76 power. So remember now, this time is representing half of the initial amount. So just like the 34-minute problem, rather than take a 5.76 root on both sides, we can just convert them into fraction exponents. So that will be half to the 1 over 5.76. Because remember now, denominator is telling you what's the root. My root is 5.76 roots. Okay. So let's see what my A turned out to be. Parenthesis half, of raising to parenthesis 1 divided by 5.76. 6 decimal place, 0.886621. Okay, so that's my growth rate. 0 point something power. So now, how much of a 7-gram sample of titanium-51 will be left over after 7 minutes? So my model, so let me write down my model. What's my actual model? My model is the amount after some time t is equal to the initial amount, whatever the initial amount is. Remember now, it's not 100%, times my growth rate, 0.886621, raising to the t power. So the 5.76 is only half-life. Okay, I'm using that number to help me to find my growth rate. So now what happened, how much of a 7-gram sample? So if I have 7 gram start out with times my rate 886621 after 7 minutes later. Okay, this is the rate, this is a decay rate for the half power. Seven times 886621. Oops, sorry. Raising to the 7 power. How much is left? Round to 3 decimal place. 3.015 grade. Okay. So this is something that I'm not really explaining, is what's the difference between when the growth rate is 0 point something versus something that is actually 1 point something. This example in the bacterial problem, we found both A is 1 point something. 1 point something is actually a growth rate, because right now all my exponents are positive. Because earlier I mentioned, if the exponent become negative, it's actually population decrease. But I can also have population decrease based on basically looking at my growth rate is 0 point something or over 1 point something. Okay, by holding the exponent as positive, or by looking at this particular model here, when that number in front of the t on the exponent is negative, where the e is 2 point something, but I'm having a negative t power. That negative tell me it's going to be a decrease. Okay, but this is this particular example is limited growth. Okay, where it will reach a certain amount and then it will stop. Okay, so there is something going on here with these type of numbers for the for the A. Because remember, 0 point something times itself 7 times is even smaller. Even smaller times whatever will still remain small, and that's how we know this problem is a decay or decrease. Okay. Alright, how much of a 7 gram of sample remain after 4 minutes? So I'm changing my 7 to a 4 minutes. So that will be slightly more, I'm pretty sure, slightly more what's left of it compared to the 7 minutes. Okay, it's decaying, it's decaying. Alright, I'm going to stop it right here. And in the next video, I'm going to begin with another types of exponential function, another type of application for exponential function. Okay, thank you for watching.